Are you guys ready? So the reason that I started looking into the header heap was that we had performance problems in H2 related to the usage, their usage of header heap. So when I actually, from my first read of the code and understanding how it works, actually I got really excited to, I wanted to, like a typical developer, I was ready to rewrite and redesign the whole thing and do it much better, and was thinking to make it more easier to maintain. But then as I started digging deeper and understanding the features and their usage, I realized that actually we can do some changes now before without currently blowing up the universe. And it seems to me that we can understand all the features and how they're used better before we decide to rewrite the whole thing. And this is what I wanted to share some of my findings. So first, I wanted to give you some background what header heap is. So it's header heap is used to store all the headers during the transaction. It's like a local storage, and it is also involved into marshalling the HTTP headers into and from the ATS cache. So examples of objects that are stored in the heap are the HTTP request response elements like URI methods, reason, and then HTTP headers. Header heap also supports storing raw data, which is not currently used. Maybe it was used in the past, but I couldn't find anywhere that we use this. So just like an overview, I just wanted to mention that there are actually two heaps. When we talk about header heaps, there are two parts, two different interfaces, and they're usually used together. So the first part is the object heap. So we have objects related to headers and the URL, the header fields, the header itself and the URL and the response. And we have raw objects, which are randomly sized chunks, which I didn't find any usage currently. And the other part is the string. It's a string heap, which is basically a different heap, which is a reference by objects, usually in the object heap. So there are two typical use cases for the header heap. The first one is probably was the most popular one when the header heap was created. It was basically storing HTTP header in HTTP1. So the way it works is that we create the heap, and it grows as we add new headers to it or new objects. And then usually in HTTP1, we don't remove or we don't modify the header enough. So everything, the heap doesn't really grow that much. It is actually meant to grow exponentially as we run out of memory. So the second usage is when we started working on H2, we use it for the HPAC and QPAC header compression uses it. So the interesting thing about this is that to enforce the size of the table required by the standard, the HPAC and QPAC code keeps adding and removing headers a lot.
Hey, Concho, are the slides supposed to be moving?
Do you see header heap usage slide?
We only see the title page.
Oh, I'm sorry. So, do you see the slides now?
Yes.
Okay.
Yeah.
Okay. So you didn't, basically I went according to the slides, so you heard most of the important things. So what is the problem basically? Why we had performance problems with the H2 was that exactly this addition and constant addition and removal of the headers, and which led to the header heap to grow exponentially basically in memory. So header heap is like inside has a linked list structure that actually we add new heaps when we run out of memory. So if we keep removing and adding objects, the way the header heap works is that we never actually remove objects, we just mark them empty. And we never use those pieces of memory, we just allocate new. So if you constantly remove and add new header fields, for example, header heap will start growing and growing. So when I'm saying this is actually just for the object heap. For the string heap, we already do coalescing. So if we run over a threshold of free space, we coalesce all the strings into one heap again, which we don't do with the header heap, with the object heap. And this is where the problem was. So if you take a look at this graph, so the purple line is the memory allocated, the physical memory that is allocated for the heap. The green one is the size of the heap, and the red one is the size of basically of the object stored in the heap. So this graph is from 10 HTTP requests, HTTP2 requests, and you can see that the memory starts growing even with 10 requests, actually starts growing exponentially. And the red line stays basically the same. We don't really, which is what it should do. I mean, HPAC actually requires us to keep a constant size of the memory. So of the table that it uses for the compression. So Masaori actually had a workaround for this on in the HPAC, but it seems that we can actually address this at the header heap, so we can get rid of the workaround later. So if you see the next graph is like 100 requests. So you can see the red line is like something small, really small, like 2K below, and this thing is growing and growing, and imagine 1 million requests. So, okay. All right, so I was thinking like at some point I realized that actually we can try to avoid the exponential growth based on the fact that actually most of the objects stored in the object heaps are with fixed size. The interface to the header heap allows us to specify any sizes or any types. I mean, even the types can be of different sizes, which is strange, but maybe at the time it made sense. But in our usage, we never do that. So we always allocate by using fixed sized objects. So I thought if we somehow get advantage of that, we won't be losing memory. We can actually reuse. The only exception is that the raw data is not fixed size. It can be any size, but since we don't use it, and we can have the code actually work with that too, I think that will not be a problem. So I decided to try to change the allocation strategy to reuse old, already deleted blocks in the object heap. So I played with different combination of different like approaches, parameters, like whether to defragment versus, I'm currently with defragment, But I thought, I mean, I experimented with and without defragmentation, like partial defragmentation, full defragmentation, and then basically different times of when we defragment. So I got really good results with no defragmentation at all, and reuse the first deleted object, and then I had some logic inside that guarantees O1 deallocation tracking, so it will not impact the performance. And then this graph is basically showing how that with 10 requests, the physical memory allocated to the header heap doesn't grow. And then next one is, this is like 100, and I check the million requests is the same thing. So the size of the objects is the same, and the size of the heap doesn't grow. Another thing with another problem with exponentially growing header heap was, before I forgot to mention, that it can get really slow at some point, because we keep allocating new and new and new features. So every object allocation will take longer and longer at some point. For example, after 1 million requests. So what is next? I'm still actually digging into this. I mean, I'm almost ready with the PR, which I think I'll probably push soon. I need just to test it well, because this change would touch everything. I also decided to avoid making changes in the marshalling and marshalling to reduce the impact of the change. Managed to keep track inside without changing the physical image. I mean, the image on the disk. Also, I have some more ideas for things to check. For example, string heap. Although we call less now, it seems to me that if we use it to remove and add headers or objects very, very actively, we a lot more often than we would if we didn't do that. So I'm currently looking into ways to tune that threshold. And also, if I start increasing that threshold, then we'll end up with more wasted space in the disk, since the current implementation actually saves the lost space on the disk too. So maybe I can manage to basically remove that space from the disk and not impact. I can go with any threshold if that's necessary. That would require a change. It will not be backward compatible with the current cache. But again, this is more like I still explore things to find ways to improve and understand the problems before I actually start redesigning and blowing up the whole thing. It seems that there are so many usages that actually needs to be investigated. So this is what I had.
Is there any questions?
Looks good.
Yeah, it'd be good to see the PR and see exactly the details of it in the code. Cool. And did you have any like benchmarks, like any CPU usage or anything like that that's being increased? Or I just saw
no, not yet. I mean, I'll probably do more, but okay. I just benchmark to the extent to guarantee that there is no worsening of the speed.
Yep. Okay.
And so far, I don't see. In some cases, actually, it's faster.
Mm-hmm.
But
yeah, I can see that, especially if you're doing a lot of requests. Yeah.
Right. So with my main objective was not to make it worse.
Yep.
Improve the memory consumption without impacting the performance. The time performance.
Cool.
Yeah, I might want to talk to you offline about the memory and stuff that is flip swap, which touches in similar areas here. It was another attempt to improve heap memory allocation handling inside traffic server. although it was more focused on the arena, what the class in arena.h rather than the string heap.
I mean, we can talk about it.
Okay. Next, is there any more questions or?
No, it looks interesting.
Okay. If not, then I think Susan, you're up next with certificate loading.
All right. And yeah, like I'm completely over now.
Yeah, we are 30. Well, actually, I think we gained some time. We're 33 minutes over now.
All
What do
right.
you want me to do?
Oh, I sent you the link to my slides, so if you can share the screen. Yeah, I'll try. I have 30 minutes, but I should.
Here, Gancho, stop sharing.